Today we're going to do in the lab a molar volume of butane prac, and this is so that you can approve Avogadro's law. And we have two people helping us, Paige and Stuart. Paige and Stuart. And the first thing we're going to do is talk about what we need in order to do this prac. So we are going to use a lighter. This lighter is a normal lighter. It's full of butane liquid. It's under pressure so that when you press the release button, it comes out as a gas. So today I'm going to get Stuart to help me with collecting that underwater. So over here we have a setup of a tote box that's full of water right to the top, and we've previously filled this right to the top so that there is no air bubbles and tipped it upside down. So that's full of water, and what Stuart's going to do is put his hand into the water, have the butane lighter underneath the opening that he's lifted this up so he can get his hand under there, so that he's got to be careful because there's a nozzle at the side which might let in some air, and he's going to press this down until this is full. But you might want to check that you can get your hand under there without letting water in. And then the very first thing, that has to be done is we must weigh the lighter and the gas before we start, because we're going to weigh how much we've collected afterwards. So Paige is doing that, and she's going to write it in the data table. So the first thing you do on your balance at home is make sure that it's on 0 and then put it on. Okay, so we've got that. And once we've used it, we'll have to dry it and reweigh it. So now Stuart's going to, first of all, see if your hand will fit underneath without releasing. Right. And he's going to press the release valve. It's not easy, actually, it's quite difficult. And I don't know whether you can see that, but the bubbles are coming up. And as the bubbles of butane are coming up, it's pushing the water down. So this is called collecting gas over water. When you collect gas in this method, you also get a little bit of water vapour, which we're going to do some calculations today to accommodate that water vapour, and that's another law, and we're going to be covering that in a minute. So today, I'll write it on the board, we're going to use Avogadro's law, which is 1 mole of any gas occupies 24.5 litres at SLC, which is 25 degrees Celsius and 101.3 kilopascals, or 22.4 litres at STP, which is 0 degrees Celsius at 101.3 kilopascals. So that's Avogadro's law. We're also going to do a couple of other laws. What's another law, Paige, that we're going to use? Do you remember what it's called?
Charles' law?
No, we're going to use
combined gas law.
Yes, thank you, Stuart. The combined gas law. Combined gas law. Do you remember what that is?
P1 multiplied by V1 over T1 is equal to P2 multiplied by V2 over T2.
Excellent. And we're going to use this to convert our data that we collect today into standard, to prove Avogadro's law, into the standard conditions. And the last rule that we're going to do that I haven't talked about yet is called partial pressures. And that's the one we're going to use to work out how much of our gas is water vapour. So that is PT equals P1 plus P2 plus P3, dot, 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 dot. Okay, 3 laws. So how are we going? Yes, it takes a little bit of time to empty the butane into this measuring cylinder. The beauty of having a measuring cylinder to do this in is once Stuart has finished doing that, we can make a mark. That's what this is for, the permanent marker on the side to indicate the volume, and then we can just let the water run out and the gas run out. You could only let the gas go in an environment like this if you didn't have a naked flame. Of course, if you had your Bunsen burner going here and you let a whole lot of butane gas go at once, it might be dangerous. So we are completely free to let this go and it's going to be okay. And then we can see how much volume we've collected, and Paige will be putting that into the table of data. So have we got a spot for that? No. So don't use this. We will use this or any of those.
So volume.
Excellent.
Switch it.
You're getting tired, aren't you? Yeah, it does hurt after a while. You might have to change fingers because holding it down for that period of time, it does take a little while. So now that Stuart has got all of the gas out, or there's probably still some gas in, it doesn't matter. We've got a substantial amount of gas. The more gas you get in the tube, the more accurate it's going to be. So here you can see he's got nearly to the end, and then what you do is you get your permanent marker and make a line so that now it doesn't matter if you were to let this go because you know how much volume that's taking up. So you can tip it up, and then what you can do is read the scale, but you've got to read it backwards. The other way you can do it, and this is probably better, is fill that up with water and then remeasure it. But we can see what it is, can't we, without doing that. So if we draw this line around to where the scale is, you can see there's inaccuracies, can't you? Which is something for you to discuss in the questions or in the discussion. So we have, what does that say? Please, you read it to me. And Paige is going to record it.
From the very bottom up to there, 470 litres. From the very bottom there,
Yeah,
all the
that's
way
right.
up.
470?
470.
470
Milliliters.
millilitres. 470, not 4,700. 470. That's right.
Yeah.
Okay. So what we're going to do now is we're going to measure the weight of this. Now this is the tricky and you can see the most error is going to happen here. This is what the paper towel is for. You have to dry this very, very thoroughly and try and get all of the water out of all the nooks and crannies, but this, once again, it gives you something to talk about, doesn't it? And you make sure it's dry, and then you ask your assistant to weigh it, or you get yourself to weigh it, and you write down what it is now. Hopefully it's lighter. Yeah, good. Ah, get it? Lighter. No. 20.6 grams. All right. So what do you do from here? We're going to use this data to prove Avogadro's law that the molar volume of butane is 22.4 litres approximately, because we're not quite at 25 degrees. So we've got our volume of butane. What we have to do now is consider the fact that the method by which we collected the butane was over water. And when you collect gases over water, by this means here, it's inevitable you're going to get some water vapour amongst your gas, which is going to throw your results out. So on your actual prac, if you have a look, you'll see on the second page there's a table that allows you because it's a standard table. It allows you to calculate how much water vapor you would get at a particular temperature if you collected the gas over water. So what I've done is, because it's 25.9 degrees and not nice and even like 25, I've worked out approximately how much is going to be between those two figures of 25 and 30 if you're reading across millimetres of mercury. What you do is, there's a 5-degree gap between 25 and 30. You then work out the gap between the corresponding millimetres of mercury, and you divide by 5, and you get every degree is equal to 1.6136 millimetres of mercury. We want to know how much 0.9 is worth, so we find out how much 0.1 is worth by dividing by 10 is 0.16136, and then we times by 9 to get this figure, and then we add it to the 25. So that if you're reading on the table, at 25 degrees, the pressure due to water vapour is 23.756 millimetres of mercury. The extra 0.9 we've worked out as 1.4522 millimetres of mercury. We add those together to get, at 25.9 degrees Celsius, this is how many millimetres of mercury the water vapour would occupy in that collected sample. So 25.20824 millimetres of mercury. The other way you can do it is graph this data and read off the graph. But this is a way of doing it without graphing. So this is how many millimetres of mercury, and then you need to convert your millimetres of mercury into kilopascals. So in order to do that, you need to know this, and I'll just highlight it with a different colour. And these are things you need to know. They'll probably be in your data book that's attached to your exam. So 1 atmosphere, these are all ways of measuring pressure. 1 atmosphere equals 101.3 kilopascals, which equals 760 millimetres of mercury. So what does that mean? If we're converting this first to atmospheres of pressure, then we would go, here's our millimetres of mercury that we calculated the water vapour would take up, divide it by 760 millimetres of mercury per atmosphere to now change it into atmospheres. This is how many atmospheres you get, 0.033169 atmospheres. If you want to then change that into kilopascals, at 25.9 degrees Celsius, you times it by 101.3 kilopascals. You can see your atmospheres cancel and you end up with kilopascals as the units, and you end up with this. I know it's very long-winded. Now this is just the pressure of the water vapour that's mixed up with your butane, pressure of water vapour at 25.9 degrees Celsius. I know it's long-winded. This is the type of thing you're expected to do. And then what you do is use yet another law. Dalton's law of partial pressures says that the total pressure of that gas is equal to the component pressures. So we've got P1 is the pressure of our butane, and P2 is the pressure of our water vapour, and we don't have a P3, do we? It's just those two. So therefore, PT is atmospheric pressure, because that's why we're doing it, 101.3 kilopascals. P of the butane, P butane, we don't know, but we do know P of the water vapour is 3.360 kilopascals. So if we rearrange our formula, the formula being PT equals P1 plus P2, and we, well, sorry, I should say P but, shouldn't I? P but and P water. And we rearrange this such that P but is the subject, equals PT minus P water, which equals 101.3 minus, what is it, 3.360. And the answer is, someone?
$97.94.
97.94 kilopascals. So that is our actual P1 from our experimental data. That's the P1. That's called dry hydrogen. Dry hydrogen. No, not dry hydrogen. Dry butane. It's been a long day, but you can leave that. It's okay. Dry butane, isn't it? Dry butane. And why is it called dry butane? Because you've taken the water off it and now it's just the butane. So this is our P1. Put it here, P1. So now we can work out, convert our volume to standard conditions. So we've got 470 mils in these conditions, but we want to know what the volume of our gas is in standard conditions. So when we want to change something to standard conditions, we use our combined gas law. So, will I do it over here? I will. I'll put it in a different colour. So, P1, which we just worked out, yeah, I'll do it over here. P1 is 97.94 times 0.47 over our T1, which was 299.05 Kelvin, and then times by T2, which was 273.15, divided by P2, which is 101.3. And that should give us our V2. So hopefully people are working that out on their calculator. Now, because the temperature is slightly more for our experiment, the volume when we're converting back to standard should come down a little bit. It should be slightly less than 4.47, but not very much.
$0.415.
Do you agree with that? Excellent. So you can see that with the new pressure of working out not with the water vapour, but just using dry butane, you get this new volume, and also it's been adjusted to be at 25 degrees. So now that we've standardised it, because this is the volume of the dry butane at 25 degrees Celsius, we can now do the molar volume, because molar volume means how much volume per mole. We haven't got per mole of butane, we need to calculate that. And how do we do that? How do we do that? So how many, do we have the mass of our, once you have mass you can convert to moles. So we have the mass of our lighter plus the butane, and we have just the mass of the lighter. So can we work out the mass of our butane? Right, so that's another thing to add to this table. Mass of butane, and it equals 21.5 minus 20.6, and what is that?
$0.9.
0.9 grams. How do we change mass into moles, when you know that moles equals mass in grams over molar mass in grams per mole, that's how you do it. So we're doing it for butane, moles of butane is 0.9 grams over, now the formula for butane, I had it written up here, I'll check it off, is C4H10. So the molar mass is 12 times 4 plus 10. So somebody do that for me. Got to do it in the right. 58 is the bottom.
Yeah.
So 0.9 divided by 58.
0.0155.
That's how many moles we have. We want to know per mole because we're trying to find the molar volume. So going back over here, we have the volume of dry butane at 25.9 and it's per, what do we say? 0.0155 moles. Do you agree? Of butane? So if we want per mole, we just do that calculation and we'll get the molar volume. Therefore, the molar volume of butane, someone got it for me, equals that divided by
26.774
for litres per mole. So this was our real experiment that we did. We had a lot of errors as you were watching, you could see. Instead of a molar volume of exactly 24.5 litres, we've got 26.774 litres. Now it's understandable in these conditions. Now you should be able to tell me what is the very next step we should do. Do you remember? Once you've found this and it's not quite right, what do we do?
Find the percentage error.
Percentage error, because we're trying to prove Avogadro's law, which says per mole of butane should be 24.5 litres and we got 26.77. So the error, percentage error, therefore error. Who can tell me the formula?
Theoretical error minus experimental error divided by theoretical error times by 100 in absolute value.
Yes, very good, thank you. Theoretical times 100. So it's going to be, the theoretical was 24.5 at 25 degrees litres. And we're taking away what we got, 26.774 litres, absolute, over 24.5 litres times 100. I hope that's not too small for you to read.
9.28.
So the error was 9.28%, which is getting up there, isn't it? But we did have quite a lot of error, and also this was a team effort. When you go to do it yourself, you might be able to be much more accurate and get that down a little bit more. So the very next thing you would be asked to do if this was an exam is to say where the errors come from.